Okay, these are some more notes for section 4.5, and this is the second example. And we have f of x equals the cosine of x, and we're going to use this x for the center of my linearization to be pi over 2, and we want to approximate the cosine of 1.75. All right. And pi over 2 is about 1.57. If you divide 3.14 by 2, you get 1.57. So you see 1.75 is close to that, so we should be able to get a pretty good approximation. So let's take a look at this. So first of all, again, the linearization, we're going to find the linearization and then use it to approximate this. So that would be your directions, and these are the same that are in your book, so you can just look for the directions. So again, my x is going to be pi over 2, so what will my y value at my point of tangency be? Well, that's going to be pi over 2, and if I take the cosine of pi over 2, which is just 0, I get pi over 2, 0. So that's going to be my point of tangency. What's the slope going to be at that point of tangency? Well, I take the derivative, and I get the derivative of cosine is negative sine of x. And then if I evaluate that at the x value, pi over 2, the sine of pi over 2, remember, is 1, and that's going to be just negative 1. All right, so there's my tangent line. In other words, here's my slope, here's my point, so I just put this in the point-slope form. Y minus y1 equals m times x minus x1. Just remember that, right? Y minus y1 equals m times x minus x1. Okay, so I pop that right in there. So this is y minus y1, in this case y1 is 0, equals m, which is, this is my slope, m. I should have labeled that, that's a slope, m, minus times x minus x1, which is pi over 2. So there's my tangent line. And then I just solve it for y, which is easy enough. This 0 just drops out, and this is my negative x, negative pi over 2. So this is my equation of the tangent line in y form, and all I do is call this L of x, and this is the linearization. That's all there is to it. So that's the linearization. Very straightforward, okay? No problem. It's just, that's about all there is to it. It's just a tangent line. Okay, now what we're going to do is we're going to evaluate this at 1.75. All right, and it's not too bad. I mean, we're going to do this without a calculator, so I kind of did a lot of it without a calculator. I actually even used this number in my error rather than the book. The book used a calculator value, and I just used my actual error value. So you'll see, I mean, my approximation value. They used the calculator to come up with the approximation, and I thought that was a little bogus. So what I did was I kind of worked it out. So how would you work this out without a calculator? Okay. You want to find the cosine of 1.75. All right. We don't have any tables. All right. So basically, we know what we know from above, and we could do that without any tables. You just on a tablet someplace if you want to work that out. So I've got negative 1.75. This was my x. That's what I want to approximate, plus pi over 2. Now, what's pi over 2? Well, pi is 3.14159. I know that many digits. Over 2, and if I do just long division, 2 goes into 3 once, remainder 1 goes in there 5 times, remainder 1, 7, it goes in there 0 times, and then bring down 15, 5, 15 goes in there 7 times, 14, remainder 1, 19 goes in there 9 times, 18, there you go. So there, see, I can figure that out with long division. I don't even have to write anything down. So let's evaluate this. What's negative 1.75 plus 1.57? So we take the sign of the larger, which actually would be negative. Sorry about that. That ends up being negative. The sign of large is negative, and the difference. And I can subtract those. I know how to subtract. So I take the difference. I had to borrow some zeros and stuff, and there's your difference. So there's your approximation. So that was actually the linearization. That's the approximation. So we don't have any tables. That's a good way to approximate that if you're out in the field with no calculator or your batteries ran out. Now, how close was I? Is this going to be a pardon me? This is going to be a good approximation. Well, remember, the error is just the difference between f of x and L of x, or the cosine of 1.75 and my linearization of that, my approximation. Well, I look up the cosine of 1.75 in my calculator. I get negative 0.17824605556, and this is my little meager approximation here. And if I actually just take the difference of these, and I did do this in the calculator, I got approximately 9.64 times 10 to the negative 4. That was approximate, because I had to round off that. So how close was I? Well, again, this is like a 1 with 1 over 1 with 4 zeros in the bottom. So I've got 1, 2, 3, 4 zeros. I think you can see that. 9.64. 9 is less than 10. So this fraction is less than this fraction. Now I can cancel one set of zeros, or a 0 on the top, 0 on the bottom. So now I've got 3 zeros on the bottom. I put this up on the top, so I got this. And that's the same thing as 1/1000th. So I'm within 1/1000th of the actual value, and that may be within my tolerances of my problem. Okay, so might be okay on that. So that's 10 to the negative 3, so we could say the error is less than 10 to the negative 3. So that's all there is to it. So again, remember, linearization is just the tangent line at a particular point, and hopefully that's going to be close enough to what we're trying to approximate, so we'll be in good shape. Again, one more thing, just to go back, we'll look at the first example. Again, notice that as my number here, my number that I want to approximate, gets farther and farther from my point of tangency, notice how the distance becomes greater and greater in both directions. And the same thing in this graph over here for the example. As I get farther and farther away from my point, my approximation, my tangent line, or my point of tangency, then I have much greater error. So I'll lose my accuracy as I get farther away. So we want to be pretty close. So we want to really pick an A that's going to be close to what we want when we find that point of tangency. And that's the trick. Okay? All right, so I hope that helps. And you only have 6 problems to do, and I'll get those solutions up for you, so it should be pretty easy.